and then we can get this laptop set up in the intervention. Yep, yeah. Right?
Okay. Sometimes you can have a whole box of guys. And none of them.
Yeah. I'm excited for your talk. Thanks for agreeing to come speak tonight.
Yeah. Like, I've been promising for a while. It's like, okay, let's get this done.
That's the spirit.
It's a new talk. Let's see how it works.
What? What? Oh, good. Has it been helping posting this stuff? Is it harder for a public audience or easier? I feel like there's less pressure.
Relatively less experience.
That's interesting. I didn't think about it like that. Oh, good. Right. Yeah, that makes sense. Oh. We have not clickered? Hey, Charlie.
Did you want to change the video at all? Like the brightness
Hey, Steven.
contrast. I changed it a little bit. I put everything back to 0, but if you think it looks better with your...
How's it going? Thanks for coming. We can make room around here. Charlie's there. I'll be here.
We can definitely put
You guys can scoot. Yeah. And you get 3 people there, picture.
I know, I'm pretty wide.
pretty wide.
Would be losing the space.
Got them elbows.
What did we calisthenics? They're donation based.
Should we pass it back? Yeah, I'm ready.
They're donation based. You can pay nothing for your hot dog tour.
Charlie's in charge of helping pass it. Hello, everyone. Welcome to Astronomy on Tap. Thank you for coming. I don't know if you remember me, but I'm back. I will be getting through the week on that. Thank you. I don't know if I told you, but so this summer I was gone doing a research collaboration. Fun fact about that is that the person advising me on that collaboration down in Los Angeles is going to be coming to give an Astronomy on Tap talk in November. Yeah, so I had a whole summer to wear him down. Yeah. But all that aside, we have a really great program planned for you. The first speaker of the evening is going to be Charlie Willard, and the second speaker of the evening will be Professor Tom Quinn, and I'll tell you more about them in a little bit. But for now, we're going to pass out some trivia sheets. If you want to play trivia, come get a sheet and a pencil from either Sam or from Charlie, and we'll get started in a little bit. Thank you.
Hello. Sheets for me, pencils for Charlie. Oh yeah, of course. Sheets are here.
Hey, how's it going?
It's too tall.
Was the audience like supposed to like keep?
I know so they spend their line. Sorry.
I know maybe a quarter. But you know, they were small pockets. A lot of them. Very
Oh,
just fun.
okay. That is really exciting. Okay. Well, it's fantastic to have professors here taking that and I think it's really good to have like a mix of different groups.
Yeah, I know. I'm very appreciative to you, Jess, and Matt McQuinn for agreeing to give AOT talks so soon.
Oh, sheets.
That means a lot.
I feel like we're a little low on I feel like there's a good number of grad students, a good number of
We got
faculty.
a new crop coming.
That's true.
So,
To be fair, though, there are less postdocs. Like, I can name, like, Pedro has given talks, Yakov has given talks, Zoe Todd, you probably don't remember. She was a postdoc in UF. She's not here anymore, but she gave a talk. Like, so we do get them sometimes, but it would be good to see more. And defending them. I wanted more faculty representation, and Tom stepped up to the plate.
here we are. So did Jess and so did Matt.
And so did Jess, and so did Matt.
So there we are.
Yeah.
So they've signed up for future.
Jess and Matt will be next month.
Okay.
Yeah.
Wow.
It will be.
I am very.
I don't think that's happened in my entire time organizing AOT, which has been going on 3 years now.
Is it third weekend?
October 23rd. Don't tell me. Don't do it. Don't do it to me. Don't do this.
I'm gone.
Yeah, I can't do this by myself.
I've been gone first.
Which means you have to cancel your plans. Right, we'll have to check in on that. And then technically, the speaker in November, who is my research rotation advisor, will be here because Vicky offered to give him the funding to stay the extra day. So I give her brownie points for that. I give more faculty brownie points for that.
lot of people. I tried last quarter and I got ignored. Every email I sent was ignored. That's okay, Tom, because you're here now. So I forgive you. We'll try again for spring, though. Do you have a microphone? Yeah. We'll go when you're back. Yes. Yeah, family fun. Yeah. Yeah. Did you just ask for a trivia slip? No, you may not. Stephen, I'm still traumatized. We were all sitting at a table with our friends who were doing trivia, not astronomers. We're just sitting with them. They win, and then we got food. Yeah. Our friend stood up and she was like, she won. And this was back when Tyler was organizing AT, and he was like, wait, that whole table is astronomy grad students, and everybody booed. I was like, we didn't help her. Good to go.
Wait. Remind me. All right, welcome again to AOT. It is my pleasure to see you all here. Does everybody have a trivia sheet that wants one? It's like talking to a brick wall.
Thank you.
Okay, so we're going to get started with trivia while I try to also extend the microphone. I think most of you know how trivia works, but I'll go through it anyways. Up on the screen, I'm going to put 10 trivia questions. Since it's finally dark outside, I'm not going to read them to you. I'm just going to put them up here. You'll have 30 seconds a question to write your answer down on your trivia sheet. At the end, I will go back through all 10 questions, but only for 15 seconds apiece the second time. So you have 2 opportunities to get your answers down, and then we will collect your trivia sheets and move on to our talks for the evening. Any questions? Once again, any questions? Thank you. Gosh, okay. Now it's time for cosmic pirate trivia.
There's 10 straight questions like that.
Oh my God. Or some nuns are going to
Yeah, I think from question 1 to question 10, like filled.
Probably. That should be the next one. We'll make that the bonus question.
You just see comprised of objects. Think of it as layers. So this speaker one, speaker one. Got the object. Live speaker. I noticed the second there. I would thought of the camera object. Background. I was like really microphone. Object is falling out. I'm like, good guy rounding over. Prep things over here.
It's the immortal grave. Galaxy, wait, that's. Oh, I love this one. Galaxies. Seven seas. That's for sure.
Webster has one.
Okay, well then just mark either of them right.
I'm not one. We're technically part of the one's just I don't know. I haven't. I feel like
Yeah, and that's wrong. But then it's wrong. Oh, you're so fine. You're so fine.
We'll find out in a second.
Okay, that was the first round. Now we'll do each one again for 15 seconds. Did Mario like the breakthrough?
that was the best sleuthing I've ever seen. Good round.
I think so. Mario tends to like and repost our tweets on Twitter, and I think we should start a Twitter battle with him where we're like, you keep talking to us on Twitter, but when are you gonna show up here and get to talk? Let's do it. could still win with 7.
He would like to.
Oh, absolutely. Absolutely, yeah.
I think we can give you some prizes to take home if they do well.
But if they don't do well, you have to bring it back.
We need a signed score sheet.
Yeah. Yeah, this is about academic integrity.
Yeah.
Wait, where are the prizes?
Oh, they're under the table.
You've got them?
Yeah.
Tobin told me to bring some stickers, and I did not bring those stickers.
Were you jerking slides?
Yeah, we were definitely very low on it.
Are you ready?
Okay.
Yeah.
Okay. And Sam's on it?
Yeah.
Okay. Hopefully you got all your trivia answers down, and if you could bring your sheets and your golf pencils to the front. Also the golf pencils, please. We will collect those and get started.
I will take the sheet and the pencil here. You. I'll take the sheet, pencils in the bag. Sheet, pencil in the bag. I will take the sheet, pencils in the bag, please.
Charlie, what's moving 125 megaparsecs per hour?
Oh, it's per H. It's the Hubble constant inverse normalized.
That's a lot. Several C.
Take the sheet.
That got me for a while.
There you go.
Beginning of last year.
Too many hands, okay.
No worries. Oh, there you go.
Everybody? Okay.
All right, last chance to get in your trivia sheet. We're about to get started.
Ready?
All right.
Seems like we're all set. Up, trivia sheet. Yeah, get it up here. That's it. I'll take it. Thank you. Where's your golf pencil?
You get shut.
I'm just kidding. I trust you. Okay, so without further ado, at this time I'm going to introduce our first speaker of the evening and our first talk. So about to join me on stage, I am saying as he stands up and walks over to the microphone. This is Charlie Willard. Charlie is a PhD student at the University of Washington Astronomy Department. He got his bachelor's degree from the University of Chicago. And he is going to be talking to us tonight about where we are in the universe. Did I do that right? Yes. Oh, good. Here's Charlie.
Cool. All right. Is the microphone working online too and everything? Good. Okay. Cool. Hi everyone. I'm Charlie Willard. I'm a second-year PhD student here at the University of Washington. All right.
Close to the.
Closer. All right. Is that good?
You can
Perfect.
Let me make it taller for you.
I can. Okay.
You can do it down here. Just keep talking. Pretend I'm not
Hello. Okay. Hello, everybody. Well, let's get right into it. I'm going to be talking to you tonight about where we are in the universe. And that's a really vague question, so allow me to elaborate. I really want to give people a little bit of a sense of scale. We live here on planet Earth. We're familiar with the things that we interact with every day, things like buildings, cities, countries, and our one singular planet that we're all very familiar with. But the universe is a lot bigger than that. And so what I want to try to give you an idea of is something in between planet Earth and the observable universe. We're familiar with lots of different sets of scales, things on the size of meters or yards or kilometers. Oh, sorry. All right. I'm used to a lot of movement. I'm wearing another like microphone too. Okay. And what I want to try to give people a little bit of an understanding of tonight is what does the whole universe look like? When we start to zoom out, what is the stuff that exists on all of the different scales between planet Earth, which is pretty small in sort of astronomical scales, and the observable universe, the entire thing. And so we're going to do a little bit of zooming out tonight. Think about like Google Maps when you start to zoom out. And more than just sort of listing off things that exist in the universe, I want to try to put some numbers to it. I want to try to give you some numbers to sort of try to understand the scales that we're talking about. And so we're going to need to build some sort of cosmic ruler stick. And to do that, we're going to need two things. The first of those two things is the speed of light. So the speed of light, it's the fastest thing in the universe. I think I'm noticing now that the color red is not showing up because that photon is supposed to be red. But light is the fastest thing in the universe. And it moves at sort of imperceptibly fast speeds on the scales that we live on here on Earth. It moves at over 100,000 miles per second. And then if we take that speed and we ask how far can we go if we travel at the speed of light for a full year, we get what we define as 1 light year, which is like 5 trillion miles, which is an extremely large number, hence why we choose to use light years instead. And as we begin to talk about lots of different scales, we're going to start talking about things that are like 1 quadrillionth of a light year all the way up to 1 billion light years. But the reason we like to use light years is it connects a little bit of space and time. So when I tell you that something is 100 light years away, you can sort of think to yourself, okay, if I sort of get in a little rocket ship, and I get, it's the future, so we have really good rocket ships, and I accelerate that rocket ship to be going to the speed of light, to someone on Earth, it'll still take me 100 years to get all the way out there, even if I'm going that fast. And so when we start talking about these really big scales, we can use light years to sort of have a little bit more of an understanding of what we're talking about. But we're going to need a second thing beyond just light years to sort of build this sort of cosmic ruler stick that we're going to build tonight. And the second thing is what we in science like to call orders of magnitude. And so let me give you an example of what an order of magnitude is. This was in the quiz, so you can think to yourself whether or not you got it right. If I try to write how tall a human is in terms of light years, you can write out the decimal, which is 0.00, lots of O's, light years. But I don't know about you, that number doesn't really mean anything to me other than that it's like really small. And so what we like to do in science is we like to take all those zeros and instead write them as powers of 10 or factors of 10. So forgive the like high school class science diagram here. We like to take all these zeros that you're seeing, so these are all decimals and these are all like a billion, a trillion. And instead of all of this mess, we like to write them in terms of powers of 10. So you can write this massive number as just with 15 zeros as just 10 to the power of 15. Or you can write this number that has 6 decimal zeros as 10 to the power of minus 6. And so what we do, nope, all right, that works, is we can rewrite this number that has like 15 or 16 zeros in it as just 2 times 10 to the minus 16 light years. And what this allows us to do is it allows us to sort of put our human height on the very left side of our cosmic ruler. And each tick mark on this cosmic ruler represents an order of magnitude jump in scale. Meaning every tick mark on this ruler is a factor of 10 increase. So as soon as we go to the thing that's on this point of the ruler, we'll be 10 times bigger than a human. And so I'm going to use some things that are familiar to us to sort of get us started on this cosmic ruler. And then after this slide, I'll take some questions. So what's 10 times bigger than a human? About a building. So this is the NASA or the Google satellite image of Bickerson's brew house. And the tent that we're in is about, it's actually a little bit larger than 10 times bigger than us, but we're going to approximate for tonight. If we took 10 people and we sort of stretched ourselves across the tent here, we'd sort of get edge to edge of the tent. So that is to say that the tent is 10 times bigger than a person. But we can go bigger. Oh, there we go. Oh, too fast. What's 10 times bigger than a building is about a football field. So that's 100 meters is a football field. I tried to use Husky Stadium, but they don't have any photos that don't have the lake in view, and I really wanted the perfect up and down. So Grant, who's my brother, is here, so we get Michigan Field. And so there you go. And so that's another order of magnitude jump. So we're 2 tick marks above a person, 1 tick mark above our little brew house here. And we can just keep going. So what's 10 times the length of a football field? This is the 520 toll bridge over to Bellevue. Many of you have probably driven across it. That's about 10 football fields long. It's about a mile long. So much bigger than a football field. And then we can just keep going. So, if you drove across the toll bridge 10 times, you could drive across the city of Seattle. Width-wise, the length is a little bit longer. And then you can just keep going. So what's bigger than Seattle? The state of Washington. What's bigger than the state of Washington? The United States. And then what's bigger than the United States is the whole planet. And so the width of the planet. And so on this slide alone, we've sort of covered everything that you should be familiar with, everything that you've interacted with on a day-to-day life, except for there's obviously stuff smaller than a human, but that's for another talk. And what we've done is every tick mark on this ruler is a sort of a jump up in sort of a factor of 10 increase in scale. And so we're going to keep using this scale, and we're going to fill in the rest of this scale with the rest of the stuff in the universe. And so just remember, the difference between this point and this point is the difference between you and a planet. And so we've got quite a bit of ruler left. So the universe is going to be a really big place. So are there any questions before I move on? Perfect. I either explained, oh, there we go. That's a great question. So you notice that I was using meters, and then I switched to miles. A mile is roughly 2 kilometers. And in astronomy, at least I, who am not an observationalist, I love to round off factors of 2. If we get something roughly right, that's a really good job in astronomy. So you're right. I switched between kilometers and miles. There's roughly 2 kilometers to a mile, or a little bit more. But that was a good question. Okay, let's keep going. Let's get to the little bit of stuff that's less familiar. Maybe. Oh, there we go. Okay. Okay, so we had planet Earth, which is this, now there's just this tiny little dot here in the corner, compared to the size of planet Jupiter. Jupiter is about 10 times wider than the planet Earth. And so you might notice this dot here on planet Earth, the big red spot. That's a big hurricane on the surface of Jupiter. And it's actually like the size of Earth. So it's a really big hurricane. It'd be really, really bad if you were there. So it's really big. But even Jupiter is small in comparison to the sun. This is a red image, so it's not showing up very well. But the sun is about 10 Jupiters wide, so the sun is really big. But as we're going to do for pretty much the rest of this talk, we can just keep going. So there's nothing bigger than the sun in the solar system, but one day the sun will begin to expand as it begins to die. The sun will not sort of explode in this massive supernova like you might be expecting, but instead it will become a red giant, and so it will begin to expand. It'll get 10 times bigger than it is right now, and then it'll do it again, so it'll get 100 times bigger. And it'll actually get so big that it will grow and sort of envelop the Earth. This is where the Earth orbits, and the sun is going to get that big. Don't worry, that's like 5 billion years in the future, so it's a long way away. But you can see we've now jumped up another 2 orders of magnitude larger than the sun, which is about where the Earth orbits around the sun. There we go. So this is about the point in the talk where I stop talking about sort of cohesive objects like planets or stars, and I start to talk about distances. For example, the distance between the sun and planet Earth on this graph here. So the sun is at the center, and here's Earth. And well, we can keep going. So, all right. So, like I said, the distance between the sun and the Earth, but the solar system is a lot bigger than just all the way out to the Earth. The solar system goes a lot farther than the Earth. If we look at all the rest of the planets here, Mars, Jupiter, Saturn, Uranus, it's about 10 times further than Earth to go all the way to Saturn. Is it good? Okay. And so on this slide, what we're going to talk about is units of sort of light times time. So the speed of light times a unit of time. The distance between the sun and the Earth is 8 light minutes, meaning that the sun, as it emits light from its surface, it takes that light 8 whole minutes to get to planet Earth from the sun. And it takes that same light actually an entire hour to reach the surface of Saturn. So we're going from minutes to hours. What happens if we travel for a whole light day? We can get all the way out to the heliopause, which is like one way to define the outer edge of the solar system. It's where you sort of go from like the stuff that's in the solar system to the interstellar medium. But I'm not a solar system scientist, so I know less about that. But I do know a little bit more about Voyager 1, which is this really cool space probe that we sent out like approximately 50 years ago. Voyager 1 is the furthest object, I'm pretty sure the furthest object, and the fastest object that humanity has ever sent into space. No? But not the fastest? Okay. The furthest then. It's been traveling for 50 years, and it's all the way, it's 100 times further than the sun than planet Earth is. And it's the furthest we've explored out of our solar system with an object. And it takes light an entire day to get there. Yes, 23. Yes, this is what I was talking about. I knew that some people were going to be like, "Oh, it's not a day; it's 23 hours." Like I said before, you know, that's a lot less than a factor of 2. We round that off. Okay, so, all right, you know, you're familiar with a day. What happens if we go all the way out to an entire year? 1, 4. So you don't. Well, it's actually 4.3 in case anyone wants to correct me. 4.3 light years out to the next star. So the closest star to us is Alpha Centauri. and it is 4.3 light years away. And so I like this slide because it really starts to give you a sense that already, when we're talking about the scale of the solar system, the speed of light is becoming sort of finite, meaning it takes a certain amount of time, times that we are familiar with, minutes, hours,